I'm Saeki from Toyama Prefectural University in Japan. Today, I'll show the research results of single sensor gas discrimination and quantification based on level temperature modulation method. First, I introduce the state of the electronic nodes as a background of our study. E-nodes is expected to contribute to many fields such as healthcare and quality control of food and cosmetics. However, a compact E-nodes can only discriminate a limited number of orders, while GCMS, which can discriminate various orders, has a large size and power consumption. Therefore, miniature, low power consumption, and highly accurate E-nodes are desired. Second, I'll explain the structure of E-nodes. E-nodes generally consist of a gas sensor array and extracts each sensor response as a data vector. Order discrimination is done by data processing and pattern recognition of the data vector. Then, if the data vector is extracted and enough information for order discrimination is obtained by using a single sensor, the size and power consumption would be greatly reduced. Next, I'll explain the metal oxide gas sensor, which is typically used for the sensor array. It detects gases based on the change of electrical resistance caused by the transfer of conduction electrons when gas is adsorbed or dissolved on the sensor surface. In addition, it is known that applying a periodic waveform to the heater to periodically modulate the sensor temperature improves the selectivity depending on its temperature and frequency. Then, it is possible to build the data vector even for a single sensor, such as extracting the frequency component of the sensor response when temperature was modulated periodically. Therefore, the amplitude of heater voltage and the frequency of heating are key parameters for this sensor. Conventionally, the waveforms with fixed amplitude and frequency, like sinusoidal, is employed as heater voltage. If the information of gases for various amplitudes and frequencies can be obtained from a single sensor, it becomes practical to construct E-nodes by a single sensor. Then, we have proposed a method of employing a modulated waveform whose amplitude and frequency vary periodically. This means that gas information for various amplitudes and frequencies can be obtained from a single sensor, obtaining significant information for gas discrimination from a single sensor. Recently, we demonstrated the promising property of the modulated waveform for temperature modulation. However, in a previous study, only a kind of the modulated waveform was employed and it was not optimized. Then, in this study, we employed several kinds of modulated waveforms with different parameters and investigated the discrimination with high accuracy by parameter optimization. Furthermore, employing the optimized waveform, we attempted to simultaneously discriminate the gas and quantify the gas concentration. In this slide, I explain analysis procedures. In this study, we try to discriminate the gas and quantify the gas concentration using the same data. Here shows the procedures. The sensor conductance was obtained when a modulated waveform was employed as a heater voltage. In gas discrimination, the waveform of the sensor conductance was normalized by its maximum value, and the spectra of the normalized conductance were obtained by fast Fourier transform. Then, the data points of spectra were extracted to build the data vector, followed by principal component analysis, and then gas discrimination was carried out by k-nearest neighbor algorithm. On the other hand, in quantification, FFT was conducted on the sensor conductance without normalization to obtain the spectra. After carrying out PCA on the data vectors, he examined the relationship between the PCA score and the gas concentration. Next, I'll explain the modulated waveform. In this study, we combined amplitude modulation and frequency modulation to synthesize the modulated waveforms. In amplitude modulation, the amplitude of the waveform varies as shown in the graph on the top. Whereas frequency modulation, the frequency varies as shown in the graph on the bottom. Combining these features, we synthesize modulated waveforms with periodically varying amplitude and frequency. For example, the waveform has periods with small amplitude and low frequency, and with large amplitude and high frequency, and so on. In this study, we synthesized 5 kinds of modulated waveforms. Here are the waveforms we synthesized. Today, we'll discuss details on 3 modulated waveforms due to time constraint. S1 is one employed in previous study. S2 has a smaller amplitude range than S1, and S5 a smaller frequency range than S2. This slide shows the waveform and the spectra of each waveform. First, the voltage of S1 varies in the range of from 0 to 1.8 volt, and frequency range from 0 to 60 Hz. Second, in S2, they are from 0 to 1.4 volt and from 0 to 60 Hz. And in S5, they are from 0 to 1.4 volt and from 0 to 10 Hz. This slide shows experimental methods. A MEMS semiconductor gas sensor TGS8100 from Figaro Engineering was employed as a gas sensor. The figure on the left shows the gas flow system. The sensor was exposed to the test gases of acetone, ethanol, and butyl acetate. The concentration of the gases was controlled by the ratio of 2 SLM background gas to the bubbling flow rate, which vaporizes the gas liquid sources. The range of the flow rates for the bubbling was from 0.6 to 10 SCCM for acetone and ethanol. On the other hand, it was 1.5 to 10 SCCM for butyl acetate. As shown in the figure on the right, the heater voltage was applied to the gas exposed sensor. And the output voltage was obtained by dividing power supply voltage with fixed resistance and the sensor resistance. And then the sensor conductance was evaluated from these values. Now, let's look at the waveform of sensor conductance for each of the modulated waveforms. These graphs on the bottom show the conductance for acetone labeled at several flow rates. By employing the modulated waveform as a heater voltage, the responses for various amplitudes and frequencies were obtained by a single sensor measurement. And as shown in this figure, the sensor conductance was changed with the varying flow rate, that is to say, gas concentration. For gas discrimination, the sensor conductance was normalized by its maximum value for each of the measurement conditions to suppress the effect of gas concentration. For example, these are the waveform of the normalized conductance for acetone bubbled at several flow rates when employing S5. As you can see, the effect of gas concentration on the sensor conductance is suppressed. In contrast, the waveforms of the normalized conductance shows differences among the gas species. The data vectors were built from the frequency spectra of normalized conductance for gas discrimination. The spectra were derived by FFT. An example is shown here. Then, the data vectors were built by extracting the amplitude of the spectra as shown here. The employed frequency range was determined according to the heater voltage spectrum, 0.1 to 60 Hz for S1 and S2, and 0.1 to 10 Hz for S5, in increments of 0.1 Hz. On these data vectors, we performed PCR to extract the characteristic values of each gas. The PCA plots for each modulated waveform are shown on the bottom. As you can see, each of the distributions was generally separated by gas species. Now, let's compare the results by waveform. For S1, the data of each distribution was plotted unidirectionally. It was suggested that the effect of the gas concentration was not well suppressed. For S2, it was suppressed more than for S1. However, there was a slight overlap between the distributions of acetone and butyl acetate. And for S5, the effect of gas concentration was suppressed and the distribution are plotted without overlapping. From these results, it can be seen that by changing the parameters of the modulated waveform, the distribution of each gas will also change. On these PCA plots, we carried out classification by KNN. All the data points in the plots were used as training data, and the regions of each gas were visualized. Here shows the result. The regions of the red is for acetone, blue for ethanol, and yellow for butyl acetate. In this study, we evaluated the percentage of points that are in appropriate regions as gas discrimination accuracy. The results were 95% for S1, 98% for S2, and 100% for S5. As described above, by changing the parameters of the modulated waveform, 100% discrimination accuracy was achieved for the three gases. Finally, I explained the results of the quantification of gas concentration. FFT was carried out on the central conductance without normalization to obtain the spectra. The data vectors were built similarly to the gas discrimination and carried out PCA as shown in the bottom left figure. Then the PC1 score was plotted against the bubbling flow rate. It was found that the PC1 score monotonically increases with the flow rates for all gases. This result indicates that it is possible to qualify the gas species and quantify the gas concentration at the same time. I'd like to summarize my talk. In this study, several kinds of modulated waveforms with different parameters were employed as a heat voltage to investigate the high accuracy of gas discrimination by optimizing parameters. In addition, we investigated the possibility of simultaneously qualifying the gas species and quantifying the gas concentration. As a result of the gas discrimination based on the normalized conductance, discrimination accuracy was improved by parameter optimization, and 100% accuracy was achieved by the optimal waveform. Furthermore, by also using a sensor conductance without normalization, it was shown that it is possible to qualify the gas species and quantify the gas concentration at the same time. Thank you for listening.